So welcome everyone. I hope everyone can see my screen. So today we have a really exciting topic. We will be talking about causal inference in R. So it's going to be very, very interesting. My name is Carla. I'm one of the organizers of Our Ladies Philly, and I will be the moderator today. Before we begin, I'll just go over a couple of things just for a couple of minutes. So the agenda for today, and this is a very tentative agenda. So we'll do a couple of welcome slides and announcements in the beginning for a couple of minutes. Then we will jump into the workshop, first part of the workshop at some point around 7-ish, but no, this is not a hard time. We will have a quick 5-minute break just so we can grab a drink or something. And then we will do part 2 of the workshop. And then there's going to be a poll at the end. So that's just kind of the schedule for today. For those who are new to our organization and to our meetups, Our Ladies is a worldwide organization. We promote gender diversity in the R community. We do this through meetups like this, through mentorship and other opportunities to engage with the data science community. And it's very important to us that we do this in a very friendly and safe environment. So please make sure you're familiar with our code of conduct, which basically means just be nice and friendly and kind to each other. There are multiple ways to get involved. So if you like our programs, if you like what we do, you're welcome to join our Slack community. There's a link over there. It's a very friendly group. So if you have any questions about R, or if you just want to connect with other data scientists in the Philly area, feel free to join our Slack. You can subscribe to our YouTube channel. That's where we post all of our online meetups. And if you are so inclined, you can sign up as a speaker or a mentor by going to the link on the slides. These links will be available during this workshop, and we have them available anytime. So let us know if you're interested in joining us in some way. We would also like to thank our sponsors who are supporting us. Our consortium and Independence Media have been very kind and are supporting us financially to be able to offer these meetups. All right, and a couple of announcements. So we have a few upcoming events. Our October event is on the 18th. It's about Bayesian modeling in R, so that should be another really fun one. Then we have unit testing in R in November. And then in December, we don't have a name yet, but it's going to be something about package development. So stay tuned for that. Finally, we are recording this meetup. You probably saw a little pop-up show up. So we will be recording this meetup and we will post it to YouTube as soon as we do some very minor processing and editing afterwards. So probably within a week or so. That said, also during this meetup, if you are excited about something, feel free to live tweet. We always appreciate attention on Twitter, so feel free to do that. And also, if you would like to follow along for today's workshop, go to the little URL over there, tiny URL, to get today's materials. So there's a GitHub repository, and you can download all the code and the slides. And that being said, we would like to say a huge thank you to our speaker. Eugene Lee is an assistant professor in the Department of Biostatistics at Brown School of Public Health. Previously, she was a postdoc at UPenn, and so she just recently moved to Brown. Her research focuses on developing causal inference methods with complex data. And she's even an author who has published several R packages for causal inference. She's originally from South Korea, but she got her PhD from Johns Hopkins. And like I said, before that, she was, or after that, she went to do a postdoc at UPenn. So she's somewhat local. And without further ado, I will stop sharing my screen and I will let Eugene share her screen.
All right, thank you for the nice introduction. Hello, everyone. I will share my screen. All right, can everyone see my screen?
I can see it.
All right, I'm sharing the RStudio and the Google Chrome. Can everyone see 2 screens? All right, let's begin. Hi everyone, I'm Yujin Lee. I'm assistant professor in the Department of Biostatistics at Brown University. Today, I'm so excited to lead this workshop about the causal inference using R. So throughout this workshop, I will illustrate how we can use R to do causal inference, especially using propensity score methods. So as Carla briefly introduced myself, I was a postdoc at the University of Pennsylvania in the Center for Causal Inference before I joined Brown this July. Roughly speaking, my research interests include causal inference, social networks, and biostatistics. So one of the research questions that is very relevant to my research interests is the effect evaluation of vaccine. For example, whether the vaccine A is more effective than vaccine B. And we know that the effect of vaccination may spill over from one subject to other through social ties. So this is also relevant to social networks research. Generally, I'm very interested in, or I'm very cautious about replicability and reproducibility. So I try to upload the code and data I use for my research on my GitHub repository. So if you are interested in my research, feel free to visit my GitHub. So I'm going to talk about causal inference today. Causal inference is everywhere these days. I'm not sure it's a hot topic or not, but I think it's very ubiquitous across different fields of studies, including public health, economics, social science, education, medicine. I will begin with 3 questions that are very relevant to causal framework. This day, we are all interested in the causal effect of wearing a mask on infectious rates. And the second question might be relevant to social scientists or economists. We want to measure the effect of policy interventions such as marijuana legalization on the outcome of interest, such as opioid. Can everyone hear my voice?
I can hear it.
All right, great. I will move on. Sorry about the problem. So we might be, social scientists might be interested in the effect of marijuana legalization on opioid overdoses or crime rates. For marketers, they care about the effect of the advertisement they put on online on the sales of some product. All of these 3 questions are causal questions, which means that this all care about the effect of some treatment or intervention on the outcome of interest. For example, the first question of wearing a mask is we want to compare the changes in outcome, for example, infectious rates under 2 different intervention arms, wearing a mask versus not wearing a mask. Same for the second case, we want to compare the outcome of crime rates under 2 treatment conditions, marijuana legalized or marijuana not legalized, and similar for the third case. But the thing is, to review the causal relationship, we want to say that the changes in outcomes are only due to the changes in treatment. However, often in observational study, subjects who wear a mask might have some significantly different health condition compared to those who do not wear a mask. So we cannot say that, or we cannot identify that the changes in outcomes are only due to mask wearing. So we want to compare the outcomes on the 2 treatment arms while we control everything else. So, but this is very hard question, especially using an observational study. So these are the objectives of the workshop we are going through today. The first objective is to understand the causal problem using the 3 important elements in causal inference, which are outcome, intervention, and units. And second, we want to understand the fundamental problem of causal inference. And I want to address this fundamental problem using propensity techniques, especially using R. And if time allows, I want to introduce some advanced use of R in more complex settings, such as regression discontinuity and instrument variable analysis. So I will pause here. So if you have any questions, please feel free to let me know.
I think so far no questions, but just a message to everyone, if you'd like to ask questions, feel free to ask them in the chat or on the Google Doc, and I will read the questions whenever there's a little bit of time. All right, go for it, Eugen.
All right, so as I asked before, these are the R packages we need throughout this workshop, and I want you to download before we proceed. And all the code and data are available in my GitHub repository. And during the workshop, I go back and forth between the slides and the RStudio. So I will go over the structure of the RStudio. So in the GitHub repository, you can download my GitHub repository from the link on the chat. And we have two folders. One is code and the other is data. And I also uploaded the slides I present today. So in the code file, we have two R files. One is the Lalonde data and the other is our HC data. And most of the time I will go over the code in the Lalonde data R file, but I will give you time for you to work with the RHC data at the end of this presentation. And you don't need to download the external file to work on the Lalonde data, but RHC data can be found in the data folder. So I will go over the details later while I present. So let's first work on the Lalonde data, which can be downloaded from the library matching. So the matching library is only needed in this workshop to download the Lalonde data. So you can load the library matching and load the data Lalonde, and also you can print out the first 6 rows of this data set using head function. So these are the brief snapshot of the data structure, and we have 12 variables in this data set. And among those, the treat column is the treatment variable, and the RE78 is the outcome variable. So I will briefly explain the data variables here. So the treatment called treat is the indicator of the labor training program. And the RE78 is the outcome, which denotes the real earnings in 1978. So from this data set, we ultimately want to measure the causal effect of the labor training program on the real earnings later. And you can print out the number of rows of this data set, and we have 445 subjects. And among those, 185 subjects were treated, which means that their treatment value equals 1. I denote the treatment variable by A. So treatment A equals 1 denotes that the subject is under treatment group. And the rest of 260 subjects were control, so their treat value equals 0. As I said before, the outcome variable is the real earnings in 1978. RE78 is the outcome variable. And the rest of 10 variables in this data set are covariates. So we have covariate X, including age, education level, race, ethnicity, and the others. And you can actually see the details of the variables from the matching R documents. So to explain the causal effect or to define the causal effect of interest, we need the additional concept of potential outcomes. We have 2 potential outcomes in this data set because we have binary treatment, and we denote Y0 as a potential outcome under control, which means that the outcome that will be observed if a unit gets a control. And similarly, Ya equals 1, simply Y1 is the potential outcome under treatment, which means that the outcome that will be observed if a unit gets a treatment. So each unit can have 2 potential outcomes. So the causal effects are basically the comparison of these potential outcomes. For example, the contrast between the potential outcome under treatment and potential outcome under control. But there are some problems to identify these potential outcomes with this data set. So this is the 5 individual in the Lalonde data. I just print out the first 3 subjects in this data set and the last 2 subjects in the data set Lalonde. And first subjects were on the treatment group, so their treat variable equals 1. and we observe their real earnings, which is the outcome. So we can observe their potential outcome of the treatment, which is the outcome that would be observed if they were under treatment. But we don't know what would have happened if they were under control, because these are the missing value. And similarly, for the last two subjects who are in the control group, we observe their potential outcome under control, but we don't know their potential outcome under treatment because we don't know what would have happened if they are in the treatment group. And we don't have any missingness in the covariates, so all of the variables are available. So the individual causal effect is often defined as the difference between the potential outcome under treatment and potential outcome under control. But for each row, it is impossible to identify this individual causal effect because one of them is missing. And similar for the average treatment effect. So we cannot average out the potential outcome under treatment because some of their potential outcome under treatment value are missing. And similar for the potential outcome under control, we cannot average all the value of this column because these values are missing. So this is the fundamental problem of causal inference. We have all the observed outcomes, but there are no missing value in Y value, but there are missing values in the potential outcomes. And the causal effects are defined through potential outcomes, so we cannot identify the causal effect without further assumptions. So we need other additional identification assumption to estimate and identify the causal effects based on observational data. For example, we are going to assume this, we are going to add some assumption like if unit I and unit prime has the same covariate values such as H, their expectation of potential outcome under treatment will be the same. So we can guess this value based on what we have observed from other subjects. So through this workshop, instead of individual causal effect, which is represented like this, we are going to aim for the average causal effect, which is the expectation of all the potential outcomes across different individuals. But there are two types of average causal effect that are often used in research. The first one is average treatment effect, which is sometimes called ATE. So this is the same as the average causal effect I show in this slide. This is the relevant estimate when there is a potential to disseminate treatment to entire population. So entire population is our target population. So we can ask the question, what is the effect of the labor training program on the earnings for everyone in the population? So in this case, AT is the right estimate to target. However, sometimes treatment can be only distributed to the subset of the population. Then ATT, average treatment effect on the treated, might be the relevant estimate. So this is a meaningful effect when only a subset of entire population typically receive the treatment. So the relevant question to ATT is, what is the effect of the labor training program for those who were already in the program? So you can see that in this quantity, we are conditioning on A equals 1. That means that for those who are already in the treatment group, what will be the average treatment effect, which is the subtraction from the difference between Y1 minus Y0. So maybe based on this observation, you may think that what if we can just compare two average outcomes? What if we just compare the average outcome under treatment versus average under control? So we can do that with the observed data, right? So first comment, print out the average of the outcome value for those who are in the treatment. And the second comment, print out the average outcome for those who are under control. And you can see that there is a significant difference between two average outcomes. We can actually perform t-test based on that. And the t-test results reject the null of no difference between these two average outcomes. But this is not about the treatment effects. I will explain why. So the first comment, which is the average outcome under treatment, is not the same as the marginal expectation of the potential outcome of the treatment. And second comment here is actually the potential expectation of potential outcome under control for those who are already in the control group. And this is not the same as the marginal expectation of potential outcome under control. But what we often want to measure is this marginal expectation. So, but this equality holds when A is randomized, when the two potential outcomes are marginally independent with a treatment assignment. So we can just ignore this conditioning part. This can hold when we randomize the treatment assignment. But in this case, we cannot randomize a labor training program. We just observe their treatment assignment. So often the assignment may depend on the potential outcomes. So this independent relationship will not hold. For example, those with higher income under treatment can be more likely to receive the treatment. That means that the higher the potential outcome under treatment value, the probability of A equals 1 would increase. So instead of these marginal independent relationships, we are going to relax this condition. We are going to relax this independence relationship by conditioning on X. So what this conditional independence relationship says that given the observed covariates, the potential outcomes and the treatment assignment are conditionally independent. That means that if the unit I and J have the same observed covariates, their potential outcome will be independent with their treatment assignment. So I will just print out the hypothetical 2 units by modifying the Lalonde data. The first unit is under treatment. So as I explained, their potential outcome under control is missing. And the second unit here is coming from the control group. So their potential outcome under treatment is missing. However, if their covariates are the same, I would like to say that the potential outcome under control for the first unit will be the random perturbation around the potential outcome control for the second unit because they share their covariates are the same. And similarly, even though the potential outcome under treatment is missing for the second unit because they are coming from the control group, I want to use the potential outcome under treatment for the first unit to say something about this value. And often epsilon 1 and epsilon 2 here are random. But in practice, it is very hard to find a pair of subjects whose covariate values are the same. So we want to find the groups of individuals whose distribution of X are similar with each other from each of the treated and control groups, and then compare within those groups so that we can compare apple and apple, not apple and banana, because their distribution of X are similar with each other. So
let me just interrupt for a second. There are a couple of questions.
All right.
So, because I think this is a lot, and especially for people who are seeing this for the first time, it's a lot. Could you go over what A of I means? So basically the treatment, and how do we have how do we have outcomes for the same individuals? So what is A of I, and how do we have Y of I of treatment 1 and Y of I of control?
So that's the point of the fundamental problem of causal inference. That's a really good question. We often have one Y, which is one outcome for each individual. But what we ultimately want to compare is for the same unit, what will happen if they're under control versus what will happen if they were under treatment. If we compare 2 different individuals, there might be some factor that affect the outcome. So we cannot say the changes in outcomes are only due to treatment. We only compare the changes in outcome when we change the treatment assignment and we want to control other factors. So the best way to do that is we just observe the changes in outcome using the same within the same unit. However, these values are missing because we don't know what would happen if they are under control. So we have 2 potential outcomes for each unit, but we only observe one of them. Does it make sense?
Yeah, I hope so. I think this is one of those really tricky conceptual problems when it comes to causal inference.
But that's a very natural question. So people say this potential outcome as a counterfactual outcomes because these are not real, but these are the close to what we ultimately want to know.
Yeah. Thank you. And then another question is what is marginal expectation?
So marginal, sorry about going over the details without explaining. So marginal expectation means that we want to average out all of the individual in the data set. So we want to marginal expectation of the potential outcome means that we want to average out all the individual in the data set. But the conditional expectation is conditioning on the subject are treated. We just want to marginalize the outcomes. That means that we just take the average of these 3 units because these are the only subjects who are under treatment. So compared to the marginal expectation, conditional expectation is just take the average for a subset of the population we have in the data. But the marginal expectation is we average out all the individual in the population.
Got it. Thank you. And then one request is, because this is a lot, if we could go a little bit slower on the slides so people can take it in.
Yeah, that sounds great.
Excellent.
All right. So so far we have discussed, I introduced very abstract concept of potential outcomes, but these are counterfactual, these are not observation, but these are these are the concept we want to estimate eventually. And the problem, maybe what makes causal inference difficult is we don't observe all the potential outcomes. I discussed two average causal effect depending on the research question you're interested in. So if your target population is the entire population in your data, you can use ATE. If your target population is the subject who are already in the treatment group, then we have to aim for ATT. And these estimates become important when you implement R because you have to specify what is your target estimate, what you are aiming for. So I just explained that the average of potential outcomes are not the same as the average outcome under treatment because treatment assignment might be correlated with the potential outcomes. So I just, and then additionally, we can relax the identification assumption to identify the potential outcomes, even though we don't observe them. So the important concept in causal inference is confounding. I just briefly reviewed that if the units are different on many factors, they may confound the causal effect. That means that we cannot identify the causal effect because we cannot tell if the changes in outcomes are due to treatment or the other factors. Maybe someone who wear a mask may be a little bit maybe healthier than someone who don't mask or vice versa, that we cannot identify the effect of whether the changes in infections rates are due to wearing a mask or not. So these factors are called confounder. The confounder is the variable that is associated with treatment assignment and the outcome. So this arrow is the causal effect we want to identify, but because of confounder, we don't know whether the association between the treatment and the outcome are due to treatment assignment. So the propensity score methods that I will go over today is basically about how we can control these confounders when we want to estimate the average causal effect. So I just want to recap what we have discussed. We really want to well define the treatment and the outcome. So because the causal effect is about the effect of treatment on the outcome. In the data example, the treatment was the labor training program and the outcome is the earning. but the causal effects are not the comparison of the observed outcomes. It is the comparison of potential outcomes. The potential outcome is counterfactual concept, which means the outcome that will be observed under each treatment assignment. So with a binary treatment, we have two potential outcomes for each unit, but only one of them can be observed. And this is the fundamental problem of causal inference. It is very challenging to estimate the individual causal effect. So we instead aim for the average causal effects. I explained two different types of average causal effects depending on your target population. One is the ATE and the other is ATT. But still, due to confounding, which due to the confounder, which are also associated with the treatment and the outcome, we need the further assumption to identify the average causal effects. So we want to make that the potential outcomes and the treatment assignment are conditionally independent given the covariates. So, yep. Do you have any questions?
One quick question before we proceed. So can you give examples of ATT and ATE? Seems like in general, people aren't sure when to use which.
Yeah, that's a great question. So for example, if we are interested in the effect of marijuana legalization on the crime rates, and suppose that we want to compare the Pennsylvania versus New Jersey, and we know that assume that Pennsylvania implemented marijuana legalization, and in that case, if the target population is if we want to measure the causal effect of marijuana legalization on the Pennsylvania residents, then ATT might be relevant. But if we know that maybe New Jersey might implement the legalization later, we might be interested in what will be the effect on the New Jersey in addition to Pennsylvania, then ATE might be relevant. So does it answer your question? So same as the labor training program effect. So the ATT measures the effect of the labor training program for those who are already in the program. But the ATE is measuring the effect of labor training program on everyone in population. Maybe those who are already in the program might be significantly different composition for those who are in the control. But ATT is only interested in those who are in the program.
I think there's a follow-up. So could you explain this again, please? So still due to confounding, we need several assumptions to identify the A by X, so the treatment by X average causal effect, including Y of 0 and Y of 1. I'm not sure I'm reading the full question here, I'm sorry. So in terms of ATT and ATE, then just to kind of wrap or go back to it. So you would use one for the entire population if you want to infer the causal effect for the entire population, even though you may not have observed treatment effect for everyone. The other one you'd use for if you only have a sample of it.
So I am a little confused about the question, but ATE is like, for example, in this hypothetical example, we might want to compare. We might want to know what's the causal effect of someone who were already in the treated, right? For the first 3 rows. Then the ATT, this is the ATT. This ATT is sometimes people interested in ATT because there might be no chance to distribute the treatment to someone who are in the control. But ATE basically what would be the causal effect of the treatment assignment to all the population in the data set. So we want to know what will happen for some who are in the control as well.
Got it.
Yes, and the confounding, just to follow the next question. So confounder is the variable that is associated both with treatment and the outcome. For example, in the mask wearing example, the treatment assignment is wearing a mask or not, and the outcome is some infection results. Then confounder might be health conditions or age. So someone, maybe there is association between age and wearing a mask status. And also at the same time, there might be some association between the age and health conditions. So we don't know whether the changes in infection status is due to age or wearing a mask. So we want to control them. What I mean by control is that we just want to fix the value of age and then compare the treatment and the outcomes, so that we kind of block the way that the confounder affect the outcome.
Sounds good. And then one last question before we move on about the last line on the summary slide. So if you could go over that part again.
That's great. Yeah, this is very abstract too. So we all understand that this independent relationship does not hold, right? So what this means is that if unit, in this example, if unit 1 and unit 2 have the same value of x, their potential outcome distribution is independent of their treatment assignment. So that means that this potential outcome under control will be just almost the same with the potential outcome under control for the second unit, because they have the same covariate value. Same for the potential outcome under treatment. So they are only randomly different, so that the epsilon 1 and epsilon 2 is kind of negligible if their covariate values are the same. So in this way, this is the only way we can identify the causal effect in this case, because we do not observe all the potential outcomes. But this is more relaxed version than the former case, because this means that without having covariate value being the same, their potential outcomes are just random, regardless of the treatment assignment. And this is only hold when the treatment is randomized, like a randomized clinical trial or something like that.
Got it. And this is assuming that we have knowledge or data on most of the important covariates, right?
Yes, yes. So I will explain that later. All right.
Great.
Great. So yes, A equals 1 is treatment, A equals 0 is the control in this context. So let me illustrate how we can perform causal inference with R. And this is basically the steps that to reduce the impact of this confounder X on the average causal effect estimation. So we basically want to conditioning on X. What I mean by conditioning is like with the same value of X or the similar value of X. So we want to compare the outcomes of two individuals, one from the treatment and one from the control group, with the same value of covariates, so we can learn about the potential outcome they are missing. So the first step is decide on which covariates we have to adjust for to balance between these two treatment groups. So this question, this is a question we can ask. Distribution of X are maybe significantly different between two treatment groups. That is a red flag, because that means that two treatment groups are significantly different. So we cannot tell if the changes in outcomes are due to this X or due to the treatment assignment. So often some statistics like mean or standardized deviation are used to compare the distribution of covariates for each treatment assignment group. So here I will use the two R packages. And first one is the table one. So these are the column names of the Londe data set. We have 12 covariates, including treatment and the outcome. I will answer to the question, what if they are not balanced throughout these balancing ones? That's a really good question. I will go over that later, but that's another option. We can just throw out the sample that the balance is poor, but we can kind of adjust the contribution of each unit by weighting. So we may upweight some samples, or we may downweight the samples to kind of control the contribution of each unit. So I will explain that point later. So I use the create table one function from the table one library. Xvar saves the names of columns that are not treatment and the outcomes. So Xvar contains 10 variables name, excluding treat and RE778. We need this because to create the table which shows the distribution of each covariate, stratify the treatment assignment. So this shows the result of table one when after I implementing create table one function. So for each row, it has the covariate value, mean and standard deviation, and treat 0 means the control. So we have 260 control, and we have 185 treatment. So SMD is the acronym for standardized mean difference. But I will explain this concept later, but this is basically shows the discrepancy in their mean. So the higher the SMD value, the more imbalance the two treatment group have for each covariate. So you can see that the SMD value is very high for no degree covariate. And so the mean is no degree is 1.83 for the control and 1.78 for the treatment. So they are very different with each other. We can also use the library called Cobart, and I will also introduce this package later. And in Cobart, we can use the bar tab function. And this looks like a formula, but it's just basically, we want to print out the distribution of this covariates stratified by treatment assignment, similar to what we had in the previous slide. But here we can actually specify the estimate, ATT or ATE. And M threshold means that if the statistics are larger than 0.05, then we just want to say that these covariates are not balanced between the two treatment groups. So I just draw the red box to indicate the covariates, those threshold is above 0.05. So it looks like that we must adjust for age, education, no degree, RE75, U75 covariates, because treatment groups have a significantly different distribution with respect to these covariate values. So the next step is to estimate the distance measure using this covariate and conditioning on the distance measure. Oh, I decided to choose the covariate more liberally or maybe more conservatively. So I include 8 covariates here. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8 covariates to adjust for. Great. So what I mean by measure the distance means that I just want to measure how different the treatment groups are using these covariates. So the measure of the distance measure is the propensity score. Formally speaking, the propensity score is just probability of receiving the treatment A given the covariates X. So in this X, I plug in this 8 covariates here. So since we have 8 covariates, since this is just probability, we have just a single value of E sub I. So it can provide some summary of all the covariates. And I'm going to say that within a small range of propensity score values, treated and control individual should look only randomly different on the observed covariates. So instead of adjusting for the covariate value for each of 8 candidates, we just used a single value, which is a propensity scores. So do you have any questions so far about the propensity score?
There are a couple of questions. One in the chat asking, isn't there an issue with using p-value to select covariates because it relies on sample size? In a really big sample size, wouldn't almost all covariates be unbalanced if you rely on p-values?
I'm not sure I understand the question correctly, but here I guess the p-value is based on the statistics, and statistics are the function of the mean and the standard deviation. So maybe the sample size problem can be handled through standardized deviation, because the larger the sample size is, the smaller the standard SD is. So in the second question, is a really big sample size, it would almost all covariates be unbalanced in your real life. So I don't think so, honestly, because with a big sample size, maybe it would also harder to reject the null of no systematic difference, because of the same reason I explained, this, because the variance is small, so we need more evidence against the mean. So does it answer your question?
I think so. And then let me see. On slide 23, do you have a max number of covariates you could reasonably adjust for?
That's a great question. Of course, it depends on the sample size you have, and also the number of subjects in each treatment group. Often, especially most of the social science or economic studies, the number of treated is a lot smaller than the number under control. Maybe because the treatment is often expensive or invisible to some people. So in that case, the number of treatment is very important. Maybe just 1 out of 100 people is treated. In that case, we cannot control. Maybe 10 out of 1,000 were treated, then we cannot control with control for many covariates. But often I heard that 20 to 30 is okay. But there are many machine learning methods developed so that we can kind of do the variable screening before we implement the propensity scores. That made us to choose the important covariates, even though it's very high dimensional, having 100 and 200 variables, but we can kind of do the screening procedure to choose the important covariates before feeding the propensity scores. So.
Got it. Then similar or related to covariates, so are confounders and covariates the same thing?
That's a great question as well. No, not all the covariates become confounder, because there might be some covariates that is only associated with the treatment, but not with the outcome, or the other way. They may be associated with outcome, not with the treatment, and also just covariates may be independent with treatment and the outcomes. So this first procedure is kind of like the step to choose the confounders among the covariates. So we have 10 covariates, but I selected 8 as a potential confounders.
Got it.
Great.
All right. I think we have a few more questions, but we can leave those for later.
All right, sounds great. So because I just explained the concept of propensity scores as a summary of these potential confounders into a single value. And most of the R packages implement step 2 and 3 together. So I will go over step 2 and 3 all together. So just get a sense of what the propensity score is. I fit the treatment on the covariate we have choose in our first step. Since the treatment variable is binary, I use the binomial family using GLM function. So this command line print out the fitted value of the probability for those who were under treatment. And the next command print out the summary of the fitted value of propensity score for those who are under control. So you can see that minimum and maximum is in the range of the probability, which is 0 and 1. And as you might expect that the fitted value of propensity score is larger for those who are on the treatment group. So this is the visualization of the distribution of this fitted propensity score value for the treated in the red plot and the control for the with the blue plot. So the propensity score, fitted propensity scores is more right skewed for the control group. So basically, the role of propensity score in causal inference is we want to balance the distribution of the propensity score between two treatment groups, between treated and control, to make these two groups more comparable. So I'm going to introduce 3 methods to do that. And one is subclassification and matching and weighting. The subclassification is basically very well related to the stratified analysis. So we stratified by the subclass defined by the propensity scores. Matching is just match the treated unit to the control whose propensity score value are similar to the treated propensity scores. And the last one is weighting. So I will pause here, and if I will take some questions, and maybe we can take a 5-minute break.
Sounds good. There are a couple more questions. Let me see which ones. So if we use matching, should ATE and ATT be similar or the same?
That's an excellent question. We'll go over that after this break.
Perfect.
And, yeah.
Okay. There's a question about slide 26. Can you repeat the interpretation of difference and threshold? If whoever asked this question, could you please write it out in words, and I'll ask it. Okay. On slide 28, is this correct? A propensity score is the estimated probability of treatment assignment based on the covariates in the model.
That is exactly correct.
Perfect. Okay. I will leave this here for now. I think we can take a break. And my request to everyone who's typing questions is I can't keep up between the presentation and all the questions. So please write out your questions in full words, and I will just read them off that way. It makes it a little bit easier for me. So let's take a 5-minute break and we'll resume after that.
Maybe before I move on, I will answer a few questions in the chat box. One of the questions is, what if we include unbalanced covariates in the propensity score computation? So that means, I think that means balanced covariates, because like maybe black and RE74, there is no clear difference between two treatment groups. The proportion of black is kind of balanced between these two treatment groups. That's a good question. Often that affects the variance estimation because we unnecessarily control for the covariates that are already keep the balance between these two. So it only affects the variance, and maybe precision will decrease because we spend the extra effort to fit those with the covariates. And the other question is about the matching. I think the Ross comments are mostly correct, and whether that's the estimate for the ATT or AT, I will go over those concepts when I explain the matching. But I think in this case, that's the ATT, because we fixed the treatment and define the control who are similar to treatment. So that our target population is mostly the subject who are already in the treatment group. So let's talk about the subclassification first. I just say that we want to balance the distribution of the propensity score between two treatment groups using the propensity scores. And I will go over the three methods. The first one is subclassification, which is similar to stratification. So subclassification is basically to form subclasses, and within the same subclass, we want to balance the distribution of the covariates. But it's almost invisible to balance the covariates of 8 we have. So we are going to use the propensity scores. So within this subclass, their propensity scores are very similar with each other. And also in this subclass, their propensity scores are very similar with each other. So we form 6 subclasses based on the propensity scores, and we only compare the outcomes between these two treatment groups within the same subclass. Because if we compare the treated individual in subclass 1 and control individual in subclass 6, these are not the comparable comparisons. Why we only use subclasses, 6 subclasses? This is just the default number of subclass that match-it have. So for the subclassification method, I will going to use match-it library, and within that library, I will going to use match-it function. So there is no capital letter here, but in the library, M and I are capital. So this is the propensity score formula we are going to use. And based on these propensity scores, I'm going to construct a subclass. So we can specify the detailed method using the method argument. And for subclassification, we can use subclass, and we have to specify the data set. So I save the results in MR subclass and print out the results here. So after this procedure, we formed 6 subclasses based on the propensity scores, and propensity scores are estimated from the logistic regression that I have shown before, like exactly same as this. And the target estimate is ATT, but you can specify the estimate as ATE. We use 8 covariates we have chosen from the first step. And for the detailed summary statistic, you can use summary and standardized equals true. That means that we are going to use the standardized mean difference to compare the distribution of each covariates between two treatment groups. All right, so the subclassification is another version of matching, but we have more options in matching methods. The first one is K-to-1 nearest neighbor matching, often called the greedy matching method. So in this nearest neighbor matching, for each treated unit, we select K controls whose propensity scores are close to the treated propensity scores. And the other option is the optimal pair matching, sometimes called optimal matching. And this attempts to choose the matches that collectively optimize the overall criteria. So even though it sounds very complicated, we can understand that optimal pair matching is more advanced version of the nearest neighbor matching. The optimal full matching, sometimes called full matching, chooses the number of subclasses and assignment of units in the optimal way. The exact matching is to create the subclasses based on the unique combination of covariates. So to have 2 individuals to be exactly matched, they must have the same covariate values. So they should have same age and sex. This sounds very powerful, but as the number of covariates increases, it's very hard to find the pair of individuals whose covariate values are exactly the same, especially with a continuous variable. And matching and selection can be done with and without replacement, and you can specify as an argument as far as I know, because if we match and select the matched pair with replacement, that might affect the variance estimation because we used individual twice or 3 times. So, but you can specify that as an argument. So, but the caveat here is that the K-to-1 nearest neighbor matching and optimal pair matching are only for ATT by design. Simply speaking, this nearest neighbor matching and optimal pair matching, first fix the treated units and find the control whose propensity scores are similar to the treated. That means that our target population is the treated group. And this is the ATT. But the optimal full matching and subclassification can calculate both ATT and ATE. And depending on the target estimate, we can change the argument in the function, and the detailed procedure are different whether we estimate the ATT or ATE. So I will implement the matching using match-it function. Before that, if you have any questions, maybe I take a few more. So one of the questions I can see in the chat box is why ATT or ATE?
It means to be ATE.
Yeah, how to decide which one to use? That's a great question. This is relevant to your research interest and also the availability of the treatment assignment. As I briefly explained earlier, if you know that treatment is, there's no chance that treatment will be distributed to the older population, maybe ATT might be relevant. But if you think that the treatment can be distributed to the older population, maybe the target population should be ATE. Great. And I use match-it library. So say M and I are capital and there is no capital letter in the function. And now you can see the formula as before. This is the same formula I used to fit the propensity scores. And you can see that there is no outcome variable here. So there is no RE78. This is because the treatment propensity scores are just about the relationship between the treatment assignment and the covariates. This has nothing to do with the outcome. So I can specify method equals nearest. Compared to the case when I use subclassification, I use the method equals subclass before. But now I want to use the nearest matching, and default ratio between treated and control is 1:1. So you can see that 1:1 nearest neighbor matching was done. And one thing I want to say is the exact matching can be fitted into other matching. For example, this comment implements the nearest matching for these 7 covariates, but I want to perform the exact matching with this covariate, no degree. So the results of this matching should be the pair of treated and control, and their no degree value would be the same. So you can specify any covariates you think very important here. So the exact the pairs of the individual should be exactly matched on this covariates. However, one caveat here is that I recommend not to use the continuous variable here because it's relatively hard to find the individual whose continuous values are exactly the same, like height or weight. But the no degree is the binary variable, so it's not very difficult to find a pair whose binary values are exactly the same. So I can print out the results m.out, and for detailed summary, you can print out the summary function. But I explained the 1:1 nearest matching, but we can control we can adjust the number of control units matched to each treated using the ratio argument. Now I use the no degree in the usual formula. And same as before, method equals nearest, I save the results in m.out2. So that means that I want to match two control at maximum to one treated units. But just out of curiosity, I kind of print out the number of control matches to each treated, but I just realized that not all the matches pairs have two controls, but some of the pair have one control and some of them have two controls. Also, I assume that this ratio is the maximum number of control matches to each treated units. So I will answer the latest question. Nearest matching, nearest neighbor matching is only for A to T because kind of find this nearest matching is finds the good control that are matched to the treated. So we don't know, we don't care about the distribution of control. So in this figures, we only care about the distribution of this red plot and find the blue dots that are matched to the red plot. So the target population is the treated units, which are shown in red graph. So these are the abstract explanation of the nearest matching.
Quick question about matching. So do you have a favorite go-to matching method? How do you choose the matching method for your analysis?
That's a good question. First of all, it depends on the target estimate, whether ATT or AT is the target. And also the number of control and the proportion between the treated and control units. For example, when the number of control is a lot larger than the number of treated, one-to-one matching would kind of throw away a lot of control samples, which may affect the power and the effective sample size. So the proportion of treated and control units may affect the decision. I like the full matching because first of all, I can either estimate ATT or ATE, and also I don't have to specify the number of subclasses or how many units I have to match for each treatment, but it kind of do it automatically and optimal way. I don't know the detailed procedure they do, but I kind of trust what they do because maybe someone who know better than me may develop this algorithm, and the people use it a lot.
That's great, thank you.
Yeah, so as I said, this implements the full matching, and you can specify the estimate equals AT or ATT, and you can work on how whether the results are different or not if you specify target estimate equals ATT. So I save the results in full.out, and you can see the detailed results using the summary function, but here is the snapshot of you have. So I use the optimal full matching, and I use the propensity score as distance measure. And you can also use other distance measure like Mahalanobis distance or others, but I think the propensity score is the default measure. All right. There is a question like full matching always find the matches regardless of the distribution. I don't think so. They sometimes drop the sample whose distributions are like outliers or not matched to the control or to the treatment. So for example, you can see that this is the number of observations. We have 445 is original and 445 is matched. In this case, we did not throw away any samples, but sometimes I think they do. Nearest, for example, in nearest matching, of course, because it's one-to-one matching, we actually discard some number of controls here. So if there's no question, I will go over the weighting, and probably I have to be more in hurry, but
let's do it.
Yeah, great.
And we can save some questions for the end, so we can proceed with this so that we can also try some of the code and play with that, hopefully within the time, and then we can save questions for the end.
All right, sounds great. So we discussed subclassification and matching. The last method is weighting. I like weighting most among these three, and probably I can explain why. So this is a probability, the propensity score was the probability of being treated given all the covariate value, and I denoted propensity score of each unit as E sub I. Depending on the target estimates, there are different formulas. First, for the AT, this is the formula for the weight. I denote weight as by W sub I. If unit I is treated, their propensity score weight is 1 over the propensity score. So this is why it is sometimes called as inverse probability weighting, because it's inverse of the propensity scores. For those who are in the control group, their propensity score weight is 1 over 1 minus propensity scores. And I will briefly illustrate why this works with 2 examples. Suppose that we only have one covariate, which is female or male. And since our target population is AT, we want to keep the proportion of male and female to the population level. Here, in this case, we have 22 subjects, and among those, 10 were male and 12 are females. And among 10 males, 8 of them are treated and 2 of them are controlled. Among 12 females, 4 of them are females and 8 of them are 4 of them are control and 8 of them are 4 of them are treatment and treated, and 8 of them are control. So there is a like significant imbalance between male and female proportion across different treatment groups. Then how can we apply the AT weights? So again, we want to keep the ratio between male and female to 10 to 12 in both groups. To do that, we are going to use the propensity score weighting. So I denote X equals 1 being male and X equals 0 denotes being female. So for the first stratum, for subjects who are under treatment and male, so these individuals, their propensity score is the probability of being treated given they are male. Anyone can guess this values? Maybe you can type your answers at the chat box. So what would be the probability of being treated given they are given they are male? So yes, that's correct. So among 10 males, 8 of them are treated. So that means that their propensity score is 0.8. That's correct. So the AT weight is 1 over the propensity scores, which is 1.25. And so we are going to weight 8 individuals in this stratum by 1.25. So after weighting, the weighted population becomes 10 instead of 8. And we can apply the same formula for each stratum. So for example, maybe for the last stratum, for some who are in the control group and female, so we have 8 individuals here, their propensity score is 1 over 3 because among 12 females, 4 of them are treated. So we can apply this formula because this stratum is under control. So the AT weight is 1.5. So after weighting this 8 individual by 1.5, the weighted population becomes 12. So after applying this formula, you can keep the ratio between male and female to 10 to 12 for each group. So this is how AT works. Usually, this is more complicated because we often have multivariate X. In our formula, in our data set, we have 8, but basically the way it works is similar. So let's talk about ATT weights. I will go a little faster, but now we want to keep the proportion of male to female to the treated population. So we have 8 males and 4 females. So because of the definition of ATT, we don't have to weight the treated individuals, right? Because this is a target population. But we want to keep the proportion of male and female in the control to the treatment level, not this target population level. So we are going to use this ATT weight, and we only change the formula for the control. This is a propensity score over 1 minus propensity scores. The propensity scores are same as before because I use the same distribution of this toy example, but the formula is different. So the ATT weight for this group is 0.8 over 1 minus 0.8, which is 4. So I'm going to weight these 2 individuals in this stratum by 4. So after weighting, we have 8 individuals. And similarly, I'm going to weight this 8 individuals in this control group by 0.4. So after this weighting, we have 4 individuals. So you can keep the ratio between male and female in the control group to the treatment group level. So this is how ATE and ATT weights work. So how can we implement this weighting? So I'm going to use the library weight it. So similarly as before, we have capital in W and I, but we don't have any capital letter in the function. And also this is just about the relationship between the treatment assignment, the covariates. So there's no outcome here, but this is the same formula as I use in GLM function. We have to specify the estimate here. So first, this weight that out is about the ATE weight. So you can print out the result of this weighting, and the summary actually print out the distribution of weights for the treated and control group. And you can also do the same thing with the estimate equals ATT. So in this case, the distribution of weights for the treated equals 1 because we don't have to weight the treated individuals. So we have discussed how we can use propensity scores to balance the distribution of the 2 treatment groups. We don't have to care about all the covariate values, but we only have to care about propensity scores because this is the summary of the covariates. I introduced roughly 2 methods. One is matching and the other is weighting, and subclassification or stratification is one type of matching. And before implementing each method, we need to specify the target estimate first. Either we are going to estimate ATT or ATE, because some matching methods only allow to estimate ATT, and also the weighting formula are very different between ATE or ATT. So one of the questions I can see is, does weighting cause issues if we have near 0 or really large weights? Yes, we do. It affects the variance because there are a lot of variability for the extreme case of weights. For example, some weights might have 10. That means that one sample represents 10 individuals. So the results are very much depend on that sample. So in this case, we can kind of do some trimming by extreme weights, but that is kind of the beyond the scope of this presentation. But people sometimes do trimming based on their propensity scores. Basically, just ignore the individual whose propensity score values are very large. If someone has very large propensity scores, that means that they are outliers with respect to the covariates. They have very outlier distribution of the covariates. So yeah, that's also common. But I think based on my experience, I think like up to 5 is okay, but beyond 5, maybe there might be a little problematic in causal effect estimation. So for now, you can see the minimum of the propensity score for treated is 0.5 and the maximum is 4.3. So I think this is okay. Also for the ATT weights, the control weight is 0.2 and maximum is 2. This is also good range. So the next step is to do some diagnostics. So as I explained in step 1, we use some statistics like mean difference variance ratios or t-tests to compare the distribution of covariates stratified by the treatment groups. So I think I just quickly went over the standardized mean difference in step 1, but more formally speaking, this is the difference in the proportions for the binary covariates and means for the continuous covariates across the treatment groups. And they consider the standard deviation. So they kind of do some adjustment using the standardized deviation. Often a threshold of 0.1 is used. I think I used this threshold before in step 1. That means that if the SMD is larger than 0.1 or smaller than minus 0.1, that means that we kind of, there is some imbalance between two treatment groups for that covariate. This is very similar to what we have done in step 1. So I will just quickly explain. So as I briefly mentioned, Cobalt is useful R packages that provide a balance assessment. So you can see whether the two treatment groups are balanced for each covariate before and after conditioning. So now I use the result of matching. So this is a matching I use for the first time. So this is a one-to-one matching with no degree exact matching. And you can see that some of the covariates are not balanced, even though they are kind of on the borderline. But I like this visualization better, which is the log plot that is available in Cobalt library. Because this figure automatically print out the threshold. So this vertical dotted line are denoting the threshold minus 0.1 and the plus 0.1. So beyond this line, that means that we have some imbalance. And below this line, we have some imbalance. So red dot shows the result when we did nothing, and the blue dot shows the result when we do some adjustment. In this case, after we do some matching. So you can see that after matching, blue dots are closer to 0 lines, which is completely complete balance. But you can see that the no degree had 0 difference because we use the exact matching. However, some covariates go weird. So in the different directions, I don't know how it happens, but sometimes it happens. But we can do the same thing with the weighting methods. I will show you why I like weighting better, more than matching. So I now use the W dot results. So I use the ATE weighting. So similarly, I can print out the log plot, and you can see that after weighting, the blue dots are very close to the vertical line of 0, even though we have the same imbalance in red dots. So you can see that the balance of each covariate is better with weighting. So I will quickly look at the last step in performing causal inference. So far, we only care about the relationship between the treatment variable and the covariates. Now we have to do something about the outcomes, because throughout this workshop, our aim was to estimate the AT or ATT. For subclassification, we can do two things. The first one is to estimate the effects within each subclass and then combine, or we can include subclass information like whether each individual in the subclass 1 or 2 or 6. We can use that factor in the outcome model as the interaction terms. I put the code for this subclassification for the first case in the R code, R file in my R studio. So you can check the code there, but I will mostly go over matching and weighting. So matching, after matching, we can simply run the regression model on matched samples. For example, in the regression formula, we can specify data equals matched dot m dot out instead of using the Lalonde. I will explain it later. And with weighting, we can run regression with weights that we estimate before. So how can we do the outcome analysis after matching? How can we estimate the ATT or ATE? So in the outcome model, we want to regress the outcome, which is the real earnings, on the treatment assignment. And this coefficient is related to the treatment effect we are interested in, because we use the matched data set after rematching. I think we use one-to-one nearest matching here. But you may wonder if we have to include the covariates we have used in propensity score model. The answer is yes, and it is actually recommended to include the covariate we have used before in the outcome model as well. It may provide kind of like double protection against the confounding. But only interpretable coefficients is associated with this treatment. Since the outcome was the continuous, I use a regression model, so I use the LM function here. So this print out the confidence interval from this regression model. Since the first one is the intercept, the second one is the coefficient associated with the treatment variable. So what I mean by protection is that so someone asked the doubly robust concept. Maybe it's related to doubly robust because we kind of control the covariate effect in the treatment and the outcome model. So this is a very similar concept to what it calls doubly robust inference, but this is not exactly the same. We can also do the regression model using the weighted population. But here, things get more complicated because we need extra library called survey. The R package survey allows us to feed a generalized linear model, so-called GLM, to data from a complex survey design. The reason it is complicated is that we kind of want to incorporate the weight in the linear regression. So this design, that W save the design, which means the weight. You can understand that this design save the weight we feed it from W dot out, and then you have to specify the data here. The tilde, the one, you basically you can ignore this formula. It just says that there is no cluster structure in this data set. So the only thing we have to do now is you can specify design equals design.w. That means that we are going to use the weights saved in this design. But instead of LM function, we are going to use SVY-GLM, which allow us to estimate the coefficients under this design. But the formula is the same as before. So you regress the outcome on the treatment variables and the other covariates. And the coefficient associated with this treatment variable is the ATE. So this is the 95% confidence interval of the ATE effect. So I think, I'm not sure the other methods, but ATT is a little lower than the AT, maybe not. I think the confidence intervals is wider for ATT compared to AT. It's just narrow. And you can implement the same code with W.out too, where we use ATT weights. So I plan to give some exercise for you to work on, and maybe instead of 10 minutes, probably I will give 5 minutes, and then I will go over the code with you. So we have used the Lalonde data so far, but I want to introduce another data set about the right heart catheterization data, so-called RHC data. Here, the units of analysis are ICU patients in 5 hospitals. The outcome of interest is the binary indicator for death, yes or no, and the treatment assignment is right heart catheterization or not. We also have some potential confounders, including demographic information and the disease prognostics. So these are the first six rows of this data set as before I saved the variables in XBars. So probably I will give you 10 minutes to work on after answering the last question. So someone asked question, any disadvantage of using propensity scores? Anything specifically to be careful about while interpreting results of the outcome after reading? I'm not sure what you mean by disadvantage of using propensity scores. Yeah, so sorry, I don't understand the questions. Maybe interpretation, the interpretation depends on the target estimate. So this is the one thing you have to keep in mind. Like this is the causal effect of when the target population is the entire population. But this is a causal effect when the target population is someone who are already treated. And we have assumed that all of the confounders are observed. So we cannot control the confounders that are unobserved. So you probably specify that these are the potential confounder we are going to care. But we just assume that there's no unmeasured confounders. Yep. Okay. I will give 10 minutes. Carla, do you think it's a good time to stop and then maybe give some time for?
Yeah, let's go with 5 minutes.
Okay.
Maybe 5 minutes for people to look over the code and try and run it and come up with questions, and then we'll wrap up afterwards.
Great. So even though it says 9 minutes, I will give it 5 minutes.
Sounds good. So everyone, this is your cue to pull up your RStudio and try and poke around with the code and get familiar with it, see if you can run it. We'll be around.
Yeah, and I will pull up the flow chart we have discussed, so you can actually refer to this flow chart if you have any questions. All right, maybe we can resume. So you can follow this flow chart when implementing the code. Actually, you can see the RHC data R files, and this implement the 5 steps we just discussed, from the confounder selection and propensity score weighting and matching, and diagnostic use log plot, and estimate the AT or ATT using the outcome regression. So great. So I plan to introduce some useful R packages for other design, but I will just quickly go over the few interesting design we have. I just mentioned that we have assumed that we observe all the confounders we have, but in reality we often have unmeasured confounders. But with unmeasured confounders, we can identify the causal effect of interest. In this case, the instrument variable method can be really helpful. The instrument variable is another variable other than treatment in the outcome, which has some association with the treatment, but nothing to do with the outcome. So if you are interested in, you can listen, you can visit the Coursera course, which is about the instrument variables methods, and some packages are used commonly is the ID reg or ID models. And the other interesting design used in causal inference is regression discontinuity. In this design, we can use the cutoff or threshold to assign in the intervention. For example, in this diagram, the treatment is only assigned when units blood pressure exceed 150. So after this line, units are treated, and below this line, units are controlled. And we might want to measure or estimate the causal effect of the treatment on the cardiovascular event. Under the assumption that people just around this blood pressure level 150 are just similar with each other, we can compare the causal effects. For example, in this line, the difference between these two dots can be interpreted as a treatment effect. These designs are often used in public health, medicine, and even social science. And you can visit the tutorial here. And the common R packages used is RDD and RDD tools. And regression discontinuity is similar to the difference in differences. If you might heard of difference. But other than that, the references I want to emphasize is Dr. Elizabeth Stewart's websites, which lists the software for implementing matching and weighting, and the Noah's package, cover package Vinia is also useful. And you can also visit other R workshop for causal inference and the other packages Vinia as well. So this is the end of the workshop, and I will answer the rest of the questions if you have.
Thank you very, very much, Eugen. This was phenomenal. Such a crash course in just an hour, a couple of hours in causal inference. It's a really complex topic, and I think it gave us a really good idea of what cool things we can do with it, and also how complex it is, and that there's a lot more out there that we can learn. So I think this was absolutely phenomenal. Thank you so much for doing this workshop for us.
Yeah, thank you for joining the workshop. Maybe I can answer a few questions I can see on the chat box. Yeah.
Yeah, I think so. Or we can also share. There were some outstanding questions in the Q&A doc, but it's getting a little late, and I'm thinking we can just share the remaining questions with you, and maybe you can address those offline. It may be easier.
That sounds great. Great. This is a flowchart. This is a key takeaway from this workshop. So I want to end this presentation with these slides. Thank you for listening.
Fantastic. Thank you so much, Eugen. Thank you.
Thank you.
And to everyone who's still here, if you could just answer the survey real quick, I think that would be great feedback for what you've learned, what your takeaway was from this workshop. That would be really wonderful. So this concludes our meetup today. Thank you everyone for joining. And again, thank you, Eugen, for this great workshop. Have a good night, everyone.
Have a good night.